Okay, in this video lecture, we're going to start chapter 21, which is on multi-electron atoms. Now, this is a many-body problem. So far, we've been thinking about just single particles bound to a potential, so electrons bound to, in a box, infinite well box, or we're thinking about a harmonic oscillator or something. It's essentially a particle trapped in a parabolic potential, and now we're starting to think about multiple particles trapped in a given potential. So in this case, a multi-electron, and so the potential is again the Coulombic potential, but now we want to consider two or more electrons. So let's actually start simple like that. Let's start with two electrons, and let's start with something as simple as the helium atom, and that I think will really get us a good taste of what's involved in this, because soon the problem will get pretty complicated and we're not going to be able to do any kind of analytical solution, even with lots of approximations. Analytically, we'd have to go to numerical solutions. So let's just go and look at this problem then from the first principles. So what we have then for a helium atom, and this is again assuming that we've already done the separation of the wave function into the two parts, one for the center of mass and one for the two electrons orbiting the center mass. So we're only focusing on the electronic part of the wave function, and so the electronic part of the Hamiltonian. And in that Hamiltonian, we're going to have a kinetic energy for electron 1, for maybe this guy here, kinetic energy for electron 2 for this guy there. Then we'll have the Coulombic attraction of electron 1 to the nucleus. We'll have the Coulombic attraction of electron 2 to the nucleus. And then we're going to have this guy, which is the Coulombic repulsion between the two electrons. So this is something that is really going to throw a wrench into the works, so to speak. And so this is what we're going to have to understand, like the effects of this guy. So if we go forward here, and I'm just going to sort of put my bullet points there, just sort of reiterating what we knew. It's this guy right here, this guy, the Coulombic repulsion term, which is not really a small perturbation on the rest of these guys. And normally we think, if you add an extra term onto the Hamiltonian, maybe you can sort of adjust for it by doing, say, static perturbation theory. But it turns out in this case that this is going to be really too big. And so we wouldn't be able to do static perturbation theory. We'd have to go out to so many terms, it wouldn't be worth it, right? So let's take a look at first, so just to sort of get an order of magnitude idea of what's going on here, let's just drop this term and compare what we get with and without this guy, or in other words, see what we get without this guy compared to the experimental energy. So if we got rid of the repulsion term, then we just have the kinetic potential energy of electron 1, the kinetic potential energy of electron 2, and the potential energy would just be the Coulombic attraction of the electron to the nucleus, of electron 1 to the nucleus and electron 2 for the nucleus. So we've eliminated the electron-electron repulsion between 1 and 2. So those potentials are only includes the Coulombic attraction to the nucleus. So effectively now you can see that I can write this as just the sum of two Hamiltonians, one for electron 1 and one for electron 2, and there's actually nothing in this Hamiltonian that knows about electron 2 and nothing in this Hamiltonian that knows about electron 1. So what we have here is we have two non-interacting electrons bound to a single helium nucleus. And we talked about in the previous chapter about non-interacting Hamiltonians or particles, and where the Hamiltonian can be written in this form. And what we learned was that you can write the total wave function as just a product of the individual wave functions if you're in this non-interacting particle limit, right? So for a multi-electron atom or molecules, we're going to call this the orbital approximation, where we just sort of assume that the electrons don't see each other, okay? And that's going to be called the orbital approximation. And now, following from this then, it's really simple to start using this Hamiltonian to just find that you get, because everything separates nicely, you just essentially have the hydrogen problem solved twice, with the nucleus actually being a helium atom instead of a hydrogen atom nucleus. And so what we get for the energy then is just going to be -1 Rydberg, z squared over n1 squared for the first electron, plus z squared over n2 squared for the second electron. So that's the solution, and you know, it seems simple here, and of course you know all the work that goes into getting these solutions and getting this energy, but once we have it in this form, we know for two electrons not interacting, we can just rely on that old solution, and this is what we have. And so if you go to the ground state, so that would be a case where N1 is equal to 1 and N2 is equal to 1, so the two electrons in the N equals 1 state, this expression here gives you an energy of about minus 108 or 109 electron volts. Now, if I compare that to the experimental energy, it's about minus 79. So from minus 108 to minus 79, that's about 38% error. Okay, so that's a lot. So you can see right away that just in this simple exercise that the Coulombic repulsion term is not something that's just a small perturbation on the Hamiltonian. It really is a big term compared in affecting the energy, taking it from minus 79 to minus 108 by ignoring it, okay? And that should make sense too, right? Because the repulsion term is something that's going to sort of push the electrons apart and is going to raise the energy. So the two electrons are going to be more tightly bound to that nucleus if there was no repulsion between them than if you added the repulsion. So this is a much lower energy, more tightly bound than this case here, which is the actual experimental energy. Okay. So this brings us to, what are we going to do? we can't use perturbation theory, and we need a way to kind of tackle this problem and go forward. And this is what brings us to an approach called the variational method and the variational theorem. So let's first see what this is all about, how this can help us, and then we'll see an example with, say, the helium atom, all right? So what we want to do is we're going to try to find a guess for the ground state wave function. And what's important is that we want to know, if I can guess the ground state wave function, then is there any way I can sort of determine whether it's a reasonable guess or not? Is it a good guess? And it turns out that we can set some limits on, or some boundaries on whether our guess is getting better or worse. And it works out like this. If I take my guess and I say, well, whatever my guess is, it's a good, you know, it's a guess in the sense that I've done a good job in my guess, and that it's a normalized function, it's well behaved, it doesn't have any of the sort of things that would make it a bad wave function, but we just don't know if it's the right wave function, right, or how close it is to the right wave function. But what we know is that that wave function can be written as a linear combination of the correct wave functions. In other words, the correct energy eigenstates for the Hamiltonian. These things we do not know. We do not know what the energy eigenstates are, but we do know that they exist. And since they exist, we know that we can express our guess as some linear combination of those correct eigenstates. Okay, so you're thinking maybe this is a little weird. Well, I don't really know this, so how's that going to help me? Well, let's see how this can help us set some bounds here. So we need to know these coefficients, sort of, you know, to multiply times each of these eigenstates that sum up to give us the right guess, or the guess that we have just put together. So what we know is that if our guess is normalized, then we can just take this expression for our guess, plug it in here and here, taking the complex conjugate, and we'll get this double sum where we get the product of these coefficients, Cn complex conjugate, and then Cn, and then these integrals. Now these are the integrals of the energy eigenstates, and we know these guys are all orthogonal. So we know that if m is not equal to n, that integral's gone. And it's only when m is equal to n that this integral is non-zero. And in fact, actually, if everything's normalized, then this integral comes out to be 1. So everything's as expected. So if we take this part over here, we know that this part over here will go to 1, and then we'll just end up with the summation of these guys, Cn, because now all the m is only equal to n here, and so we get down to one sum, and that has to still be equal to 1, and that tells us that all these coefficients have to add up to 1. Well, okay, that's not really surprising here, but it just shows you that, okay, that we have a set of coefficients, and they have to all add up to 1. Now, if we had made a good guess, what we would have found was that the zeroth coefficient, the ground state, the one associated with the ground state, which is the state that we're trying to guess, that one will be close to 1. If we made a perfect guess, it would be exactly equal to 1. And all of the higher n coefficients would be equal to 0. But the important thing is, note again, we just sort of proved here that those coefficients are all between 0 and 1. And a great guess would have C0 equal 1, and a bad guess would have C0 equal to 0, and maybe some other, all the guys up here would be non-zero. Okay, so let's keep going with this idea then and see where it takes us. If I calculate with my guess the expectation value for the energy given the Hamiltonian, and again, we know the Hamiltonian, what we don't know is the wave functions, the eigenstates of that Hamiltonian, but we're going to take our guess for the ground state eigenstate with the Hamiltonian, and we're going to again plug in our expression for our guess in terms of the energy eigenstates, the true energy eigenstates. Again, we don't know them, but we know that we can write our guess in terms of them, and we get this expression here. Now, again, we know that when H operates on psi n, we just get back the energy times psi n, right? And then we end up with an integral that is either 0 or 1, depending on whether m and n are equal to each other or not. So I write that out here. When H operates on psi n, I get En back, and then I get an integral of just psi n, which this guy goes to 1. Notice my double sum now went down to a single sum because we got rid of all the m not equal to n's, and then we end up with this expression that the expectation value for the energy is just a sum over all the energy eigenstates, all the correct energy eigenvalues weighted by these coefficients squared. Now, if our guess was good, and we actually guessed the ground state, then we're going to get an energy that's very close to E0. But you can see that what we're going to get, though, in generally is correctly written here as just the sum of some linear combination of all these energy eigenvalues. Now, if I take this expression and I do a little math trick, I'm just going to do something that looks maybe kind of silly here, but I'm going to add E0 and I'm going to subtract E0. Okay, you see I've done nothing to this expression here, but just add plus E0 minus E0 to this part here in parentheses. So the reason I did that is because then I can rearrange this into this form. So now I have this guy here, which is, I pull the E0 out, and then I have this guy here, which is the sum over the deviations from E0. So how far all the energy eigenvalues are above the ground state energy eigenvalue. Right? And then, of course, this guy gets pulled out of the summation, and that sums up to 1, so we just end up with the ground state energy plus this term here. Now, remember, I'm after the ground state energy. I'm after the ground state eigenstate, and I want to know its eigenvalue, which is going to be the ground state energy. And this term is the lowest energy you can have. So that means that En minus that guy is always a positive number. So a sum of all, and this guy's always a positive number, so a sum of a positive number times a positive number is always a positive number. So what I'm getting at here is that the guess that I make has to be, at best, if I made the perfect guess, equal to E0, and if I made a bad guess, it's going to have all this term here where all these positive numbers are added up to it. So that means it's always going to be greater than, or at best, equal to the ground state energy. Okay? That is the basis of the variational theorem. It set a lower limit saying that if you make a guess, your guess is always going to be higher than the ground state energy unless you guess really perfectly, and then you'll find the minimum possible energy, which is the ground state energy. So this is what's called the variational theorem. And what it gives us is an algorithm for tweaking our guess wave function to make it better and better. All right? So what we're going to do is we're going to say, put into our wave function, we have our wave function, of course, which depends upon you know, the particles that are there and all the normal things you would expect it to vary on. But then we're going to have some extra parameters, you know, kind of shape parameters that shape the wave function to slightly, you know, making it move out a little bit, maybe push this part out, just something to adjust the shape. And these are going to be essentially fit parameters. What we're going to do is we're going to evaluate this integral as a function of a, b, and c, and then we're going to pull up some kind of minimization subroutine or some algorithm that we have, and we're going to search this based on this integral for where this integral, the values of a, b, and c, and d, and so on, that makes this integral go to the lowest possible value. And then we're going to say, when we're done, then that's the values of the parameters that give us a wave function that's closest to the ground state. Okay, because so we don't have to know, this is what's cool, is you don't have to know the ground state energy to see how far away you are from the ground state energy. All you need to know is, as long as I can keep going lower and lower and lower, then I'm getting better and better and better. Okay, that's the idea of the variational method. It doesn't tell you when you've hit the energy ground state, but it does tell you that you just made a change to the graph, to the wave function, to make it better. All right. So next what we're going to do is we're going to look at just a simple example, well, somewhat simple, but at least we can do it analytically, of this variational approach at work here. So let's go back to the helium atom. We have 2 electrons, and we're going to write our wave function in the orbital approximation approach. So we're going to assume we have, you know, electron and wave function, hydrogen-like wave function 1, electron 2, and hydrogen-like wave function 2. And these two are going to be, say, the s orbital. So we're going to just take the wave function that we derived for the s orbital, which we know has, you know, roughly the right shape for a single electron orbiting the nucleus. Let's assume it has roughly the right shape for when 2 electrons orbiting the nucleus. But we're going to add into this some adjustable parameter that we can then tweak with the variational method. So what we're going to do is we're going to take the charge that's in the wave function, and we're going to make that the variational parameter. And the idea here is that, you know, when one electron is orbiting around a nucleus that also has another electron orbiting around, if the electron that we're interested in solving has an electron between it and the nucleus, then you might imagine that the electron out here is going to see less of the nuclear charge than if this electron wasn't present. So the idea is that we would expect that as we do a variational approach, this z will drop from 2 down to some lower value, because what we're doing is is creating a screened nucleus by one electron for the other, and vice versa. All right, so that's our variational wave function for the ground state. Now let's see if we can use the variational theorem to find the lowest possible energy that we get with that. So here's the Hamiltonian. So again, this is the kinetic energy and coulombic attraction for electron 1 to the nucleus, the kinetic energy for electron 2 and its coulombic attraction to the nucleus, and now we have the coulombic repulsion between the 2 electrons. Now this gets kind of messy, so we're going to go slow. So what I'm going to do is take this Hamiltonian, and right now I'm not going to use explicitly these guys. I'm going to leave them in this form of just, you know, psi h1, psi h2, just so that we can keep this all on one slide. And I'm going to put down then the integral that I need to do for the energy. Over here, the integral I need to do for the energy is going to involve electron 1, and here's just sort of the Hamiltonian that we'd have if it was a non-interacting electron with the other guy. And then we have for the electron 2, its expectation value for its energy as if it was non-interacting. But then we have to add this last term over here, which is the coulombic repulsion term, which you can see now that's going to involve both wave functions. So again, when I plug this wave function over here for psi 2, the psi 1 just sort of slid past all this and integrated away. And the same thing over here for psi 1. The psi 2 was in here, but when I set this up, the psi 2's just sort of slid past each other and integrated away because those integrals those wave functions didn't depend on any of these variables, so they just went out of the integral to their own integral, which then integrated to 1. Okay, I hope that makes sense. So now, what we're going to do is we're going to try to minimize this guy, and we have to get the form of these guys into here. So what I'm going to do is a little trick. So we have a difference between the z prime that's in the wave function, which is our adjustable parameter, and the z that's in our Hamiltonian. That's the true charge of the helium nucleus. So I'm going to rewrite the problem. So I'm going to look at delta z. The difference between z and z prime is delta z. What I'm going to do is rewrite it over here that z is equal to z prime plus delta z. And I'm going to substitute out this z and this z for z prime plus delta z. Okay? So that's going to make this term split into 2 and this term split into 2. All right, and so here's what I got. So I have the first electron, which looks pretty much like an electron interacting with the nucleus, the helium nucleus, but now you see this is just a non-interacting electron with a nucleus, but now the charge is now z prime, right? Over here is this adjustment now, because now this was z, but now we made it z prime plus delta z, so now we got a new term over here, new integral with a delta z there, involving that Coulombic attraction. And then the same thing here for the second electron. We have a z prime and a delta z over here for this term. And then finally, this term just sort of came along for the ride and didn't change. All right. Okay, so take a look at that carefully and make sure that that makes sense, what I did. Now, the first and the third term, again, these are just the sort of classic problem that we solved when we were just solving the hydrogen atom. The only difference is, if you just look at that all by itself, this is just the hydrogen atom problem, but the only difference is that we now have a nucleus that's a variational parameter, a nuclear charge that's the variational parameter z prime. That's the only difference. So we know all the solutions to this problem, and indeed we know the solutions to that problem too. Those integrals we know, right? They're already worked out for us. When we get to the second and the fourth term, well, that's just an integral involving the Coulombic attractions, but with a delta z there. So we'll have to evaluate this guy, and I'll just go ahead and plug in those wave functions here and here, and I'll leave it to you to double check all this, but if you do all that, you get something like this, and then when it's all said and done, you end up with this expression for this guy, and then of course this is a little, you're going to get more or less the same thing for that guy too, okay? All right. The final term, this guy right here, is going to really be a lot of work. So in the notes, I don't do this, okay? But I leave it for you to show this in the notes. So if you do this in the notes, I think it's a homework problem. You can show that this guy comes out to this value. Okay, so we've done it. We already know these solutions. We just calculated these. I leave it as an assignment for you to get this one here. So if I bring them all together, the first and the third are here, the second, fourth are here, and here's the fifth term from the repulsion term. So when I add it all up, I get this expression here for the expectation value of the energy. All right, now, at this point, you may be thinking, what are we doing? I've sort of lost track of what we were trying to do. Well, what we were trying to do is we wanted an expression for the expectation value of the energy in terms of some variational parameter, which is z prime in our case. And what we need to do next is find where this term is the minimum. So we're going to take the derivative of this guy with respect to z prime, which I've done right here, and set it equal to 0, and find the minimum. And the solution that you get in this case is a minimum comes at delta z is equal to 5/16. All right? So we found the lowest possible energy that we can get with our variational parameter. So we go back to this guy, plug in that value, you get this expression here, which has got to be at best equal to the ground state energy, but probably just a little bit above it, right? So if I take the helium atom, which is z equals 2, that means my z prime is 2 minus 5/16, and that becomes 1.6875. So the z prime, the variational parameter, is essentially the effective nuclear charge seen by one electron when it's shielded by the other, and vice versa. This guy is reduced down so that it's not quite a full +2 charge after the screening. So if I take that, now I have all constants in here, I can start plugging in numbers, and what I get is an answer of minus 77.5 electron volts. And that is, compared to the experimental value is minus 79, is not bad. It's actually good. It's only 1.9% away from the correct answer. And that all we did was just made one variational parameter here to make our wave function change its shape. So we really didn't do anything to the wave function in terms of the shape of the wave function. We just sort of changed, it's sort of, each one's a little attractive potential, the attractive term in that wave function. So anyway, that's the variational theorem, and that's an example of the variational theorem. So next, we're going to look at multi-electron atoms.